All right, let's take a break from our theory for a minute and look at an application. We still got a lot of theory to develop here, but here's an interesting little application of what we have so far. Let's suppose that we are asked to find the square root of 2. We're going to do it using a general method that's called Newton's method, and in general it can be used for finding the zeros of a function. So how do we apply this method to find the square root of 2? Well, first of all, find the square root of 2 means that we're looking for an x that satisfies this equation. X squared equals 2. Another way of putting that is we can put everything on the same side of the equality sign. We're looking for an x such that this side on the left is 0. So we're looking for a 0 of this function, x squared minus 2. Now right now, this is telling us we don't have it. If we had such an x, this would be a 1. We don't have it yet because we haven't completed our process. But what we're going to do now is develop a method for finding the zeros of a function, in particular the zeros of this function here, of the x squared minus 2 function. So the first thing we do is, let's go up here and define that function so we can use it in the program. And then we take the derivative of that function. We know how to take the derivative of a polynomial. We take the exponent and bring it down. So that's 2x. And we lower the exponent, x to the 1. So that's 2x. And the derivative of a constant is 0. So f prime of x is just 2x. Now, how can we find the root of the square root of 2? Well, let's look at a diagram here. Let's pick any x for a starting point. This x here, say x equals 3, and let's compute f of x. How can we get closer to our root? In our graph, this is our root right here. This is the x that we're looking for. That's where this function has a 0. So how can we get closer to that point? Well, if we look at this slope of this line here of the graph of f of x, if we were to draw a tangent line through this point f of x, that would come down something like this and hit the x-axis, say here. That would bring us closer. In other words, we want to somehow find a way to mimic this procedure here. Find a tangent line, draw it down until it hits the x-axis, and that's our next iteration. If you look over here, if you watch this thing, you'll see that it's getting closer. Let me go back to my original. See, this says we're way off. My x is not anywhere near what I want it to be. That should be a 1 if this is a true statement. But now I do my first iteration. I get a little closer. That's a little closer to 1, so I'm heading in the right direction, and you can certainly see that from the graph. So how do we do this mathematically? We've done it sort of pictorially. How do we do it mathematically? Well, let's call this little gap here, from here to there, let's call that, let's see, we want, I think it's t for text, is that it? Yes. We want to call that dx. And we want to call the gap from here up to here we want to call that dy. Alright, now how is dx related to dy? Well, if we go over here, we recall our definition of the derivative. Dy dx is the slope of that tangent line, so that's actually equal to f prime of x. That means we can solve this thing for dx. dx is this expression. Let me rewrite it. I'm going to write it as dy divided by f prime of x. But now look at the picture. Since this bottom point here is on 0, it's on the x-axis, dy is actually equal to f of x. This gap from here up to here is just f of x. So for dy, I can substitute f of x. So that's this x, that's the gap between my original x and my new x. So to compute my new x, I take my original x, which was x sub o. Let's go to this formula here. My original x was, I'm calling it x sub o. That's this point back here. I subtract dx sub o from it. But what's dx sub o? Dx sub o we just computed is this thing here. It's dy sub o over f prime of x sub o. And what's dy sub o? That's just f of x sub o. So this is Newton's method for finding the next iteration. We take an arbitrary value, we compute f of x sub o and f prime of x sub o. We take that ratio and subtract that from x sub o. And again, why do we subtract it? Because we're here and we want to come back to here. And dx is the positive difference between these 2 points. So we want to subtract that. So that got us a little closer. And then we do that again. And so this is our first iteration, got us to this x. My next iteration is going to do the same thing. I'm going to compute the slope at this point. I'm going to draw a line down until it hits the x-axis, and that'll be my next iteration. So that's going to be there, and now it's pretty close. And if you look over here at our formula, you can see we're getting closer and closer to 1. And let me do another iteration. And we're closer still. Look over here. I'm now at 9989, and one more. And so that's pretty good approximation after only 4 iterations. And we can set that up in a spreadsheet also. Let's go back to our initial picture. Our initial step is to pick an arbitrary x, compute f of x. F of x is the same as dy. We compute f prime of x, and that x is changing. Right now x is 3. The next iteration is going to be whatever we end up with down here. We compute f prime of that x. We use this formula down here to compute dy. To compute dx. We know dy, we know f prime, so we solve this for dx. That tells us how much we have to change our x by to get the next iteration. And in terms of our picture, it's this. We jump down this much. That's the dx between these 2 points there. Then we do it again. We just keep going and going and going until we see that after on the 5th iteration, we're not getting any change in our x value. So that's a pretty good indication that this is the correct answer out to 3 decimal places. If we looked at more decimal places, then we'd have to go to more iterations. And notice that let's do a bunch of iterations here. Let's go out to 4 just so we get to the solution that we have up there. So I'm at my 4th iteration. I'm showing that my my iterated value down here is x equals 1.41, and if I put more decimal places in there, it'd be 1.414. And notice I can start any place. That x that I chose was sort of arbitrary. Let me start someplace else, and we'll see what happens. Suppose I start out here. The same thing happens. I can't quite see it up there, but you take the slope, boom, that's your first iteration. You evaluate it, take the slope, boom, second iteration, third, fourth, and it zeroes right down to it. Again, now on this one it looks like we'll have to go to the 5th iteration before we get stability in our answer. So it depends on where you start how many iterations you have to take. But now notice this. Suppose I started over here. What do you think is going to happen there? If I start, say, here. Here I'm going to iterate down on the other root. So I get minus 1.414. So it makes a difference where you start, which root you find. If I go over here, let me start right here in the middle, and I don't know which one it's going to go to. Let's see. Whoa, it shoots off to, well, here it is. It took a lot to get down there. We finally made it, but it took us 8 iterations because the first one, look what happened with that first one. We're almost at the point where the slope is 0. So our first attempt shot us way out here, and it took us a while to bounce our way back to the iteration that gets us to where we want. Right now we're at 4. Let's actually work this thing and see. Watch it come on back. See, there it is, coming back slowly but surely, and there it makes it by our 8th iteration where we want to be. Now we can look at this mess here. This is because I've gone too far. I've gone to, I don't know, 10 iterations, and it doesn't exist on my table over here. Not a problem though. But let's look at another situation. This technique can be used for any function whatsoever. Now here's a function f of x. Suppose I want to know what the zeros of this function are. Well, here there are 3 of them. And let's see if I can get rid of my mess there. Okay, here there are 3 of them, and I can zoom down on whichever one I want. Let me start with this one here. If I start at my x at this point, I should iterate down to this 0. So let's see what happens as I increase my iterations. And if we look over here, we see we reach it by, at least after 3 decimal places, our 3rd iteration. So that would be one root of this polynomial. And of course we can find the others by starting closer to this one. Say, let's start right here and see what happens. And there it is, and it zooms down to 1. And I haven't made it yet with my, where do I have to go? I have to go to my 4th iteration. Oh, I should have it. So what is going on here? Oh, there it is. Okay, just didn't finish my calculations. So I get x equals 1, and that's my root. It's kind of, let's actually watch it develop. Here is our first iteration. Now our next one is going to take this slope right here and shoot us up here very close. So let's see that happen. Ooh, it actually shot us to the back of it, which is, okay, it's got us a little closer. Now this one's going to shoot us down on the other side. And then probably back again to the, oop, didn't want to do that. Okay, and then it's probably going back and forth and bracketing down on 1. Well, no, it isn't. It brackets it here. It goes below it and above it, and it sort of comes in from the top, and we reach 1. And finally, this one here we can also approach to. So we start here, and it zips down, and it shows that root is minus 0.562. So we can use this method to find cube roots, square roots, 4th roots, any root that you want. So it's a very useful method, and I use it in this program over and over again to, a lot of times you'll want to solve an equation, but there's no analytic way to solve it. So you need some numerical technique to find the root of an equation, and this is one of the methods, a very powerful method that you can use. So that's enough for the Newton's method.